Hello. Hello.
Hello. Yeah. Hi.
Good evening, sir.
Yeah. Good evening. Hi.
First of all, introduce yourself, then introduce your topic, and then start your demo.
Okay. Cool. Yeah. So my name is Chandra Reddy. So I have like my background is information technology, and I had done PG diploma in data science at INSOFI, which is located in Hyderabad, Gachibowli International School of Engineering. And my experience in industry is like I started my career as a machine learning engineer. So I have overall 2.5 years of experience in machine learning field. And yeah, currently I'm doing as a machine learning engineer in auditor.ai. So yeah, that's it from my side. And so coming to the topic wise, uh, so I used to explain today linear regression kind of problem. So let's wait. I share my screen. Yeah. Hope my screen is visible, right?
Yes, sir.
Yeah. So regarding today's topic is like what I have chosen topic is linear regression one. So linear regression, in the linear regression, I used to cover the most of the topics like what exactly means the linear regression and how we can calculate the good fit of the curve like with the cost functions and for choosing the appropriate values of beta 1 and beta naught, how we can calculate those beta values by using some gradient descent technique, and how we can handle the things like sometimes our model may get overfit or underfit. So how we can handle those things. Yeah, and after applying all these linear model and how we can say that the model is correct or it's a appropriate model. So some residual analysis we can do. So let's dive into the sessions like something like introduction. So coming to the linear regression part, it comes under like supervised machine learning thing. So here the target variable should be like something like continuous variable. So we used to predict the continuous variables by like something like sales of the product or sales of the outlet, each outlet, what will be the sales, and yeah, all those things. Whatever the target variable which we are choosing, the target variable should be continuous variable. So yeah, and when coming to the thing like so linear regression is basically something like we have learned we have learned this regression line in the childhood only, like something like linear regression is nothing but y equal to mx plus c. So here, so different professors or different kinds of articles, different kinds of research articles, they can written in different ways, like something like y equal to mx plus c as a y equal to beta 1 x plus beta naught, something like the notations will be changed. So the line, the intuition, the math behind it is it's same. So the thing is, so if we consider this graph, so let us assume this graph is there. So we have a data point, something like this is the space. So in this space, we have a data point. Assume like x-axis is something like your age, y-axis is something like your income. So as the age increases, as the income also increases, something like that. Take as an example. So these are all the data points which are there. So here, if we draw one line, y equal to mx plus c line, so here we can draw y equal to next t line. So different members can draw different kinds of things, like different types of lines like this, and like this, like this. So the question is, which one is a good fit line? So which one is the appropriate line? So here comes the question. So then we have the technique to find out whether this particular line or whether this particular line or some other line is a good fit or a best fit or not. So based on the cost function, so we have something called cost function. So cost function is nothing but it can tell the, so it can calculate the how much cost, like how much error may happen. So if we have something line like this, so let us assume if we have a y equal to a plus bx. So here we have something like this line. So here the actual point is there. Let us assume here the actual point is there. So here the predicted value is there. So if we calculate the distance between these two, the distance is nothing but an error. So we are calling it as a residual point, right? So the distance between the actual value and the predicted value. So we are calling it as a residual one. So what is the use of residual? So we'll see in the next slide. So I will explain you. Like as I said, something like there should be something y equal to mx plus b, y equal to beta naught plus b1 x plus c, right? So this is a line. So here the main aim is to we need to find the beta naught and the beta 1 value. So here the y values and the x values is nothing but your age and your income. So let us assume if you want to predict income, so that income value should be y. So the age value will be x here. So we need to find the beta naught and the beta 1 values. So how we can find the beta one? If you are finding the beta naught and the beta 1 values, that value should be if we that value should be best combination for the line. So it will give the less error. So if we input these values in the line, they must give the less error. So less error means it should be something nearer to this one, nearer, approximate or exact value. So how we can find those things? Like how we can find the beta naught and beta 1 value is the question. So here the major issue is we need to fix the beta naught and the beta 1 value. So how we can find? So we have learned in the childhood stages something like gradient descent. So based on the gradient descent, we can find the local minimum point. So at that point of time, the error will be very low and the slope value is also 0. So yeah, we'll discuss with that the gradient descent index in the next slide. So so as of now, so something like gradient descent is something like cost function is something like this. So here n will be the your total sample. Sample means number of your rows, number of data points in your data, n will be, and the summation will be like as long if the I equal to 1 for first row, I equal to 2 for next row. So that will be right from 1 to n. So up to your sample, and predicted will be nothing but this is the value. So this is the data point, and the actual y means the actual point. So this is the actual point. So now you can calculate the distance between these two, and you can find out the thing what will be the cost. So yeah, so this is the gradient descent approach, and we can find the best values by using the gradient descent approach. So the gradient descent is nothing but something the curve will look like. So this is a simpler problem. So we have taken only the parabola curve method. So there should be something different kinds of things will be there. So as we can go with the elliptical shapes also there, like something like polynomial shapes will be there. So all those will be there. So for the basic intuition, I have taken this parabola curve. So something the gradient descent will look like this. So in gradient we have two things. One is ascent and one is descent. So descent is nothing but it will travel opposite direction of the gradient. So if the gradient is here, if the gradient is pointing upwards, then it will travel downwards. So then it is called as a descent one. So the exact meaning of the thing is this one. So if it is arrow is upwards, the vector is upwards of this particular point. So it will travel downwards. So that is called gradient descent. So gradient descent is nothing but the main intuition of gradient descent is it will find the local minima. So of the differential function. So gradient is nothing but it's a partial differentiation of two variables like x and y variables. Like okay, so it is a gradient. The exact meaning of gradient. So here, as you can see here, so here it will be the local minimum point will be there at this point of time. So here will be the like your best beta naught and beta 1 values you can find at this point of time at this place. Why? Because here the slope is 0 and you can get the appropriate values from here. So this is a gradient descent intuition is there. So we have lot of math behind this gradient descent. So this is the basic optimization technique we are using for to find out the coefficient values. So this gradient descent is a base approach for a lot of optimization techniques, and this gradient descent will be very useful in the neural network part also when we are doing the neural network forward and backup propagation. So all the things the gradient descent will handle in the behind the algorithm. This gradient descent will handle all those values. So yeah, So this is the main intuition. So the aim is we need to find the values which are having low error. So that values will find out at this point of time. So at this point of me, here the slope value will be zero. As you can see the arrow, here the slope values will be zero. At that point of time, you can get it. So the thing is how we can travel here. So how we can travel to this point. Let us assume if we started here. So how we can travel to this point. If we started here, how we can travel to this point. So there should be something like step value will be there. So the step value will be denoted by alpha. So the step size is nothing but you can see if it is if you have taken alpha is a large value. Let us assume if you have taken alpha is a large value. So then it can step to there, it can step to here. So it never converges to the minimum point, as you can see here. Never diverges to the minimum point. It will travel all those away from your parabola curve, but it's not coming to this point. So if you have taken alpha value is a large, so if you have taken alpha value is a small, so then it will take small steps and it will come to at this point. At some point of time, it will take some time to come to this point. It will definitely come to this point, but it will take some time. So yeah, this is the best method is alpha is a smaller value we need to take. So we have a different technique like so if we place alpha value is small, so it will diverges to this point definitely diverges to the minimum point, but it will take a lot of time. So to reduce this time, we have an advanced technique. We have something advanced technique for this gradient descent. So we'll discuss that one. So yeah, so this is the main intuition, basic intuition of the gradient descent. So to find out the minimum coefficient values, beta naught and the beta one will be find out from this gradient descent. So the thing is, and again the thing is, something is like regularization thing. So the regulation thing is nothing but something like so you like if your function in the regulation technique, why we are using the regulation is the question mark. So why we are using? So we fit the line y equal to mx plus beta naught plus beta 1x. We fit the line. So we know that we have calculated the cost function and we have calculated the appropriate optimized beta coefficient. Then why we need this regulation? So regulation is nothing but so sometimes your model may do some things like underfitting and overfitting things. So something like if the model is saying it as a underfit, okay. So then underfit meaning is so when you are doing the training and the train test sampling, so it haven't performed on the train data as a good. So it haven't given much accuracy on the train set, but it unexpectedly or suspiciously it has given more accuracy on the test data. So there may be you will find the at that point of time that particular test points can be handled by the algorithm. In future, you are not sure that it may give more accuracy on the test points also. You haven't give any uh, judge on that model. So why? Because it has underfitted. So it has given less accuracy on the itself in the train data itself. So then then another case we have overfitting. So the model has performed very well performed on the train data, but he failed to predict on the test data. So it has given less accuracy on the test data. So then the case will come as overfitting. So overfitting is nothing but it tries to cover each and every point. As you can see here, it tries to cover each and every point. Meaning, the bubble, all the zeros are separated by the line. You can see it is very flexible. It can move anywhere. So here overfitting is there. So high bias problem is there here. Okay. So sorry, low bias problem is there. So if the bias is low, it's very flexible to move everywhere. So it can cover each and every point. So if and note the point, if we have a low bias, there should be high variance. Why? Because these two are opposite to each other. So here, if you can see here, high bias, it means you can see the curve thickness. It's not moving anywhere. It's a very standard curve. So it has high bias, low variance. Okay. So when coming to this one, appropriate fitting, this is the exact what which we need. This one. So for we need to appropriate fitting, so we'll go with this regression technique. Okay, so degradation technique is nothing but, so this is the function what we have used earlier. Up to here you have used already, right? Y predicted minus y actual whole square. Okay, so the lambda value will be the regression one. Okay, so the beta will be your things like your beta quotient, beta naught, beta one. So as here in example we have what we have two cases like age and the income. So here income will be the y value, age will be the x value. So let us assume if we have some other columns like smoker or a non-smoker or a gender. So these type of beta values will be um, added here. So beta one for income, beta two for smoking or non-smoking, beta three for alcoholic, beta four for something like. So as the number of variables increases, as the beta values also increases. Okay, beta quotient values also increases. So here the main equation is this one. So if you observe closely, observe these two like Lasso and the ridge. These are all well known. We'll call it as a L1 and L2 normalization functions. Why? Because L2 is, so we are doing the beta square here. Beta square means your quotient values will be squared here. So for their case, it's saying it as a L2 normalization, squaring L2. So if we are doing here, as you can observe here, the same formula will be there. As you can observe here, you are not doing any squaring here. You are applying simply modulus function. It means you are doing only one step. So that is called as L1 normalization function. So here the lambda means here lasso. So lambda will do means it will try to penalize the beta quotient. So if the beta quotients are increasing, if the beta quotient values are increasing, this lambda value will be try to decrease these variables. Let us assume if you have a beta value as a something like 10. Let us assume your beta, you have calculated everything and you got from the graded descent beta value as a 10. Let's keep here 10. So if the 10 value will be penalized by this lambda. So how you can choose this lambda value means, let us assume suppose like if you keep 0.1 as the lambda value. Okay, 0.1 into beta is what 10. So if you penalize this one, it will bring 10 value to 0.1 value, right? If you 0.1 into 10, it will bring down from 10 to 0.1. So it tries to penalize the beta quotient, this lambda value. So this lambda value also, both lambda values try to penalize the thing. So here the good thing is Lasso will do future selection, like it will drop the values which are nearer to the zero, drop the variables which are nearer to the zero. Variables means nothing but columns. Here the feature selection is happening, like feature extraction or feature engineering is happening here, like selection of columns. So here it whatever the beta values which are nearer to zero, those are not dropped by the ridge regression. So here we are not doing any feature selection, feature extraction. So that will be done by only Lasso. These two are the things which we have so far. And the thing is, you let us assume you have done entire things like you have fit the model, you have collected the cost, and you have done the gradient descent. You have done the regression techniques also you have done. So that's the last you need to perform the residual analysis, like how model is good, how much the model accuracy is good, how model behavior is there. So there's something we have a residual analysis. So for this residual analysis, we have something basic assumptions we have, how linear regression model is said to be a good fit or a good curve. So some assumptions like assumption one is like model is linear. So something like a zero residual line, the regression line will be something. If you plot the residuals, residual is nothing but the distance between the actual point on the predicted point. So those values we have given here. So that should be zero residual line. That this regression line will be. And assumption two will be, so the error terms are independent. So they won't depend on the each and every point. So there should be some independent will be there, as you can see here, residual points. Here they have independent, here they have dependent positive correlation, here they have dependent negative correlation. You can see here. So as we can go to the assumption 3, so the error term should be homoscedastic. Homoscedastic is nothing but some line, residual line will be there. So the upper area and the lower area, the mean and the standard deviation all should be same across the line. If this line increases, this line increases, this line increases, here the mean and the standard deviation, the entire thing should be same. So yeah, that is adjustment 3. And adjustment 4 will be the residual errors. What are the errors are which you have taken for each point? So those errors should be follow normally distributed curve, like normal distribution curve. So yeah, these are the 4 assumptions. You can take it as a consideration for whether your linear regression model is good or not. Yeah. Yeah, that's it from my side. Yeah.
Thank you, sir. It was very nice demo. Now I can't say anything without having the words with my seniors, but we can. You can get the feedback about the demo within 2-3 days. Okay.
Okay. Okay. Cool. Yeah.
Thank you.
Yeah. Thanks.